Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 6 of Oscillations. So let's begin with today's class. In today's class we are going to discuss about the oscillations of a loaded spring. Let's have a look how it oscillates and what would be the formula of it. Let's consider that a spring having a negligible mass which is fixed at one end and it has been loaded with mass m. If this spring is being pulled on one side and it is going to be released, it executes to and fro motion about the mean position. Let's suppose x is going to be the displacement of the mass m. Then at any instant of time t, the situation is something like this. I hope you can visualize it. Yes, this is the spring having spring constant k, and this is the block having mass m. It has been rested by this support. So if this is the situation, then at any instant of time t, restoring force F could be calculated as F is equals to minus of k into x, where k is the force constant. Then we have the relation that is equals to F is equals to ma as a second relation, and we have the relation it is equals to F is equals to minus of kx. So from this two, I can write it's a minus of k into x is equals to m into a, or from this a is equals to minus of k by m into x. According to this, even this could be written that a is proportional to the minus of x. As you can see, this is the x is equals to 0, which we call as a mean position. This is the x equals to plus a, this is what we call as a positive extreme, and this is minus a, which is the negative extreme. And this is a block m having mass m and spring constant having k. And as you can see, this it is oscillating about its mean position x equals to 0. So the oscillation of a loaded spring are simple harmonic motion because it satisfies the relation a directly proportional to the minus of x. And the acceleration of the particle in SHM at any time t is given as a is equals to minus of omega square x. And from this is equals to omega square. The omega square that should be is equals to k by m. So if such is the situation, then I can have then omega that is equals to root of k by m, and we know that omega is equals to 2 pi by t, and from this it's a t which is equals to 2 pi by omega, which could be given as 2 pi divided by omega, that could be under root of k by m. So this is t which is equals to 2 pi root of m by k. If I want to find out the frequency of this oscillations, it's an f which is equals to 1 by t, which is equals to 1 by 2 under root of k by m. This is the frequency of this oscillations. I hope this is clear. Is it clear? Is it? Great. So this is the relation of time period. Please keep this noted. This is the frequency of this oscillations. The time period of spring mass system is independent of the place and the medium. Yes, because it is simply the t is equals to 2 pi root of m divided by k. Does not depend on the place, does not depend on the time as well. Yes, and if a spring is hanging vertically and to its free end, if a body of mass m is being attached, then the elongation produced in the spring x could be written as that we have the relation, it is something like this. Let's say this is the spring, and on this free end one of the block has been attached, this is m. So a force in the downward direction is acting, which is equals to mg. A spring force is acting in the upward direction, that is what we call as in kx. So this kx is equals to mg, and from this it's a k is equals to mg by x. If I'm going to replace this, in this value, then that could be written as that this is equals to t is equals to 2 pi root of x by g. I hope this is clear. Is it clear? Is it? Are you sure? Are you? Do you have any doubts up till now? Is there anything? Is there? Is there anything? No. So factors on which time period of spring and block oscillations depends. So basically what relations we are having, if you observe it very carefully, what probability I am having is, one of the probability is either you change the mass, it's a t directly proportional to the root of m, or either you change this k, this is t directly proportional to the 1 by root of k. Other than this, I said no. So we are having this two probabilities only, that is t directly proportional to the root of m only, and it is a t inversely proportional to the root of k only. Yes, so we have two options only. I am having only two options, that either you change this or you change this, and this time period could be changed. Now how to change k? How to change k, that we have learned a little in the unit work, power and energy. We are going to revise it over here, and then we will again back to the spring block system SHM. I hope this is clear. Is it? So basically, please keep this in mind. This is the first approach, this is the second approach through which you can change the time period of the spring and block oscillations. Other than this, you are not having any options. Please keep this in mind. Now let's look how the k could be changed. Let's take one of the way, that let's suppose this is the spring. The spring is having the spring constant k, and it is having length L. Now let's suppose this spring is being cut into two different parts, and this two different parts would be of equal length. This is the situation, that let's suppose this is the length L by 2, this is the length L by 2. This spring constant k dash, this spring constant would be k dash. Yes, we need to find out the value of this, it's a k dash. So for any spring, please keep this in mind, for any spring, k into L is equals to constant. This is always constant. For any spring, k into L is constant, and if it is a constant, then what I can have is that k1 L1 is equals to k2 L2. So from this, it's a k into L, that is equals to k2, that we don't know, that means the k dash, and the new length, it's an L by 2. So as this could gone, and this k dash could be written as 2k. So this is the k dash, this is the k dash, which is equals to 2k. So this is how a spring constant could be changed. I hope this is clear. Let's do it one more time, and with certain new data. Let's suppose this is the spring, and spring stiffness is k, its length is L, and it has been divided into two segments. So totally it has been divided into three parts. This length of them, L1 is to L2, it's to L3, is 1 is to 2 is to 3. I have been asked that find out spring constants of each part of spring. This is the requirement. We need to find out the spring constant of each part of the spring. How will we do this? So what I'm supposed to do is that this is the situation. This was the natural length, or I should say initial length. It has been divided into three parts, and their length are in the respective ratios of 1 is to 2 is to 3. So this is this is equals to k into L, which is equals to constant. Yes, so let's say this is x, this is 2x, and this is 3x proportion in the lengths. So it is just the K1 L1 which is equals to K2 L2. Let's call this as a K multiplied by this length. The total length is 6L. This A is equals to, this is K2, this is equals to, this is, let's call it K1, this is K2 is to K3. Yes, so it's a K1 multiplied by, if the total length has been considered as in 6L, then only 1L, 1, it's an L. Yes, so this LL has been gone and this K1 would be 6K. I hope this is clear. Let's talk about the second length. Give me a moment. That when we do it for the second spring, then it could be written as, it is again K1 L1 is equals to K2 L2. The previous or the initial segment was K, length is 6L, and the new segment now its length is 2x, that means 2L. So this is equals to K2 into 2L. This is 2L into 3. So this K2 will be equals to 3K. This is the second part. And the third part is K1 L1 again K2 L2. Yes, this was the second, this was the third. So this is equals to K multiplied by 6L. This is equals to K3 multiplied by this segment, it's a 3x length. So this is equals to 3 into L. This is 3L, 2 is 6L. So this K3 will be equals to 2K. I hope this is clear. Yes, so by dividing it you can convert it to the new springs, and by converting it to the new springs you can have a variation in its time period. Let's look at the questions based on this. Let's suppose the situation is something like this. Yes, this is the block, this is M, this is K. If the spring is divided in two equal parts and block M is again attached to any one of the spring, find out new time period. Yes, this is the requirement. So as you see this, the initially the spring is there, a block has been attached with the free end of the spring, and if the such is the situation, I have written it's a T is equals to 2 pi root of M by K. Now as the spring has been divided into two parts, this was the situation, and this is the K and this is the L, and as this has been divided into two segments, this segment and this segment would be having the new spring constant, it's a K dash, and that can be easily calculated based on the K1 L1 is equals to K2 L2 as we have seen in the previous cases. So it's a K into L, this is equals to K dash multiplied by, as it has been divided into two equal parts, it's an L by 2. So this K dash is equals to 2K. So now the new system will look alike, that it is the new spring, it is half of the length of the previous one, and this block M, and this is K dash. So the new time period T dash, that is equals to 2 pi under root of M divided by K dash, and this K dash is equals to 2K, so this is equals to 2 pi under root of M by 2K. This is T dash. I hope this is clear. Is it clear? Is it? So can you do this? Can you do this kind of things? Are you sure? Great. Now one more approach with the springs are, we can have different combinations of the spring. They are the combinations of the spring. When I say when we say we are having the different combinations of the spring, we are having the series combinations and parallel combinations of the spring. So basically we are having the two combinations. One is the series combination of spring, and the second one is the parallel combination of spring. So let's look the series and parallel combination of the spring by one. Let's have a look at this. Yes, first it is the series combination of spring. Let's suppose this is the rigid support, and with which this is the first spring, this is the second spring, and a block has been attached. This is, let's say, K1, this is K2, this is the support. Yes. So when I'm going to pull this, and if let's say I'm having a certain external force F external, then there is a displacement in both the springs. Yes. So when springs are connected in series, force acting on both the springs will be equal, but their displacements will be different. Please keep this in mind. When any two springs are connected in series combination, the force acting on both the springs must be equal, but the displacement would be the different one. So in this case, it's an F1 is equals to F2. So let's say total extension, that would be equals to x1 plus x2, and we have the relation that F is equals to minus of kx. This minus kx represents the restoring force. So this x is equals to F by, or I should say x is equals to minus of F by k. So in this situation, this x total should be equals to x1 plus x2, and this is equals to minus of F divided by k equivalent is equals to minus of F divided by k1, plus it's a minus of F divided by k2. If this force and this force, if this has removed, then this minus 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 could be removed. So this 1 by k equivalent could be written as it's a 1 by k1 plus 1 by k2. So if n numbers of springs, if n number of springs are connected in series, then the situation will be 1 by k equivalent is equals to 1 by k1 plus 1 by k2 plus 1 by k3, and so on up to 1 by kn. I hope this is clear. So this is basically the series combination of a spring. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now let's look at the parallel combination of the spring, and then together we will have the questions based on these two concepts. It's a parallel combination of spring. How will you do this? It is something like this. This is M, this is K1, this is K2. So this is the situation, and when two springs are connected in parallel, when two springs are connected in parallel, their displacement will be equal, but force acting on it will be different. So a displacement on the springs will be the equal, but whatever the force that is acting on them will be the different one. So when force acting on it is different, what we achieved is that this is k1 and this is k2. If this is the situation, we have the relation, it's a f is equals to minus of kx and x1 equals to x2. So let's have the total force F is equals to F1 plus F2. This is minus of K equivalent into X. This is equals to minus of K1 into X. This is minus of K2 into X. So this minus minus minus, this would be the plus. And this X could be cancelled out. This X could be cancelled out. So it has been left with, it's a K equivalent that is equals to K1 plus K2. So if n number of springs if n number of springs are connected in series, then K equivalent will be equals to K1 plus K2 plus K3 plus K4 and up to Kn. Yes, this is the K equivalent. I hope this is clear. Is it clear? Is it? Do you have any doubts? Is there anything? No? So, are you ready for the questions? Have you noted this? Have you noted it down? Have you? Have you got this? Correct. Now, let's work for the questions based on this. The question says that find out time period of SHM. So the question is, this is the situation. This is block M. This is 2K. This is 3K. So what I need to do is, the time period of this situation is, this is equals to T is equals to 2 pi root of M divided by K equivalent. And when it is equals to under root of M divided by K equivalent, this will give me a 1 by K equivalent is equals to 1 by K1 plus 1 by K2. Then this could be written as 1 by K equivalent is equals to 1 by 2K plus 1 by 3K. This is equals to 3K plus 2K, which is equals to 5K divided by 6K square. This is 1 by K equivalent, and this K equivalent is equals to 6K square divided by 5K. This has gone. So from this this is T is equals to 2 pi root of M divided by K equivalent, which is 2 pi root of M divided by K, and this K, it's a 6K by 5. So this is 2 pi root of 5M divided by 6K. I hope this is clear. Is it? Correct. Ready for the next question? Let's have a look to the second question. It is the situation. It's an M and this is 4K. this is 4k. The question again same, find out time period of given SHM. We need to find out the time period. So it is simply the t is equals to 2 pi root of m divided by k equivalent, and from this it is the, as this both are connected in parallel, then it's a k equivalent. This k equivalent could be this given as it's a k1 plus k2. So this is equals to 4k plus 4k, and it simply it is 8k. So this is time period which is equals to 2 pi root of m divided by 8k. This is the time period. I hope this is clear. Is it? Great. Ready for the next question? Keep it fast. You are doing good. This is the situation. Yes, this is 4k, 4k, 8k. And I need to find out the time period of an SHM. Time period of SHM. So the situation is this is 4k, this is 4k, this is 8k, and first I need to find out the k equivalent of this, as these two are in series. Let's call this k equivalent as a k1. So this is equals to, yeah, k equivalent dash, it's a k equivalent is equals to k1 dash, or I should say it's a k1 plus k2. It's a k1 plus k2 which is equals to 4k plus 4k which is equals to 8k. This is k equivalent 1 of only this. Now this 8k and this 8k both are in series combination, so it's a 1 by k equivalent double dash is equals to 1 by k equivalent dash plus 1 by 8k. So this is equals to 1 by 8k plus 1 by 8k. So this k equivalent double dash, it's equals to 4k. Yes, it's a 1 by 8k plus 1 by 8k, which simply means it's a 2 by 8k, and if I take our inverse of it, it is just 8k by 2, which is equals to 4k. So from this it's a time period which is equals to 2 pi root of m divided by 4k. This is the time period of an SHM. I hope this is clear. Is it clear? Is it? Is it? Are you sure? Now do you have any doubts? Is there anything? Is there? No? Great. Now let's understand and learn one more concept. It's a concept of reduced mass system. What it is, let's have a look. Let's suppose we have one mass, it's an m1. We have spring connected over here. We have second mass, it's an m2, and this is the k. And if I want to find out the time period of this SHM, then as you are aware that if it is about more than one springs, we can deal with it very easily, that we will look for them, that whether they are connected in series or whether they are connected in parallel, and we want to, and we try it to find out the equivalents. But here two masses are given. When this kind of situation has been given, we use a concept of reduced mass. This reduced mass, generally denoted as mu, or sometimes it has been written as m, r as a subscript, that is equals to multiplication of these two masses, it's an m1 m2, divide by it is m1 plus m2. So this is the reduced mass, which could be given as it's m1 into m2 divided by m1 plus m2. And from this it's a time period could be given as 2 pi under root of reduced mass divided by k. So this is equals to 2 pi root of m1 into m2 divide by m1 plus m2 into k. This is the time period. I hope this is clear. Is it? Are you sure? Are you? Do you understand this? Any doubts? Great. Have you written it? Have you? Please noted it down. We are going to use it. So the situation is something like this. This is the system. This is a mass of 4 kg. This block is of mass 2 kg. And we have this. This is 2k. This is 4k. I have been asked, find out time period of SHM. We need to do this. We need to find out the time period of SHM. So as we are having two masses, what I need to do is first I need to find out the MR, which is the reduced mass, which is equals to m1 into m2 divide by m1 plus m2, that is equals to 4 into 2 divide by 4 plus 2, it's a 6. So this is equals to 8 by 6, which is equals to 4 by 3. This is the reduced mass. And as this two are connected in series, this is k equivalent will be equals to, as this two are connected in parallel, sorry, their k equivalent would be written as k1 plus k2, which is equals to 2k plus 4k, that is 6k. From this, it's a t is equals to 2 pi root of reduced mass divided by k equivalent. This is 2 pi root of reduced mass, which is equals to 4 by 3 into k equivalent, which is equals to 6k. Yes, so it's a 2 pi. This is under root of 3 6 are 18. This is 2 by 9k. Yes, it's a time period of this system. I hope this is clear. Is it? Have you done it? Are you sure? Are you interested in one more question? A very logical question and very high level of question is there. Let's have a look. Let's suppose this is the system. That this is one kind of tube, and in this tube we have two masses. This is the one mass, this is the second mass, this is m. These two are the identical masses, and they have been connected with springs. That this is one of the springs k, having spring stiffness k. Even this spring is having the spring stiffness k. The data given is, if the mass or masses m performs SHM, find out its time period. This is the requirement. How will you do this? How will you do this? What can be done? Now if you find an doubt in it, that sir, how does this performs an SHM, let's understand that you will place this here, you will place this here, and just now release it. So they will move in this direction and this direction. This is moving in this direction and this direction, and this is how they will perform an SHM. So what is to be done? What could be done? What do you think? How this could be achieved? What I understand is this is t is equals to 2 pi root of reduced mass divided by k equivalent. Now again the question is the spring. Let's call this as a first spring, and this spring, this is the spring number 2. Both this are in series, or these two are in parallel? These two are in series or these two are in parallel? How could we know this? Okay, what can you comment about their displacements? That whatever the length, whatever the expansion of this spring, it is the same compression of the spring, so their displacements are equal. Yes, and when the displacements are equal, that means these two springs are connected in parallel. So the reduced mass, that is equals to m into m divide by 2m, and this is equals to m square by 2m, which is equals to m by 2. The k equivalent, that is equals to k1 plus k2, which is equals to 2k, because both are the identical springs. So now time period is t is equals to 2 pi root of reduced mass divided by k equivalent, and if such is the situation, then this would be the reduced mass, it's an m by 2, and this k equivalent, it's a 2k. So this is equals to 2 pi root of m by 4k. So this is k divided by 2, which is equals to pi root of m by k seconds. I hope this is clear. Basically, this is the question that has been asked by JEE Advanced. Yes, but you did it. Great. Well done. Do you understand this? Have you? Have you got this? Do you have any doubts? Is there anything? Is there? No? Great. Now let's look at this question. The question says that time period of block oscillating with one of the spring having spring constant k1 is t1 if same block oscillates with another spring having spring constant k1 k2 having spring constant k2 is t2 if same block oscillates with another spring having spring constant k2 is k2, then its time period is t2. Its time period is t2 if these two springs are connected in series. Find out new time period. Yes, this is the question. Go through the data once and focus on this. It says time period of a block oscillating with one of the spring having the spring constant k1 is the t1, and if the same block oscillates with another spring having spring constant of k2, then its time period is t2. So if these two springs are connected in series, we need to find out the new time period. How will we do this? So it is with k1 spring, its a time period is t1. With k2 spring, its a time period is t2. And when they are connected in series, 1 by k equivalent is equals to 1 by k1 plus 1 by k2. This would be the situation. So let's deal with this. We know that the time period of oscillation would be given as t is equals to 2 pi root of m by k, and from this it's a t square, which is equals to 4 pi square into m by k, and it is equals to k is equals to 4 pi square by t square into m. Or if I want 1 by k, then it is equals to t square divided by 4 pi square m. this will be my master formula. I am having this, it's a 1 by k equivalent, that is equals to 1 by k1 plus 1 by k2. As they said, block remains the same. So it's a 1 by k, that is equals to basically t square. That is what I'm looking for. Divide by 4 pi square m is equals to, when block k1 has been attached, the time period was t1. It's a t1 square divided by 4 pi square m, plus this is t2 square divided by 4 pi square m. If I'm going to solve this, then this and this has gone. So the data I have been left with, it's a t square which is equals to t1 square plus t2 square, or I could have it's a t which is equals to square root of t1 square plus t2 square. I hope you got this. Yes. What was your answer? Was it same? Was it? Great and well done. Keep it up. I hope this is clear. Now, if I change the question little, let's have a look that in the previous question, if springs are connected in parallel, find out new time period. How will you do this? That if this springs are connected in parallel and you need to find out the new time period, what should be done? What I am having is this t which is equals to 2 pi root of m by k, and from this it was t square which is equals to 4 pi square m by k, and from this it's a k which is equals to 4 pi square m divided by t square. Now as they are connected in parallel, what I can have, it's a k equivalent which is equals to k1 plus k2, and if this is k equivalent is equals to k1 plus k2, what I can write, it's a 4 pi square m divided by t square. This is equals to 4 pi square m divided by t1 square plus 4 pi square m divided by t2 square. So as this is going to be cancelled, this has gone, this has gone, this has gone. So from this it's a 1 by t square is equals to 1 by t1 square plus 1 by t2 square. I hope this is clear. Was it clear? Was it? Are you sure? So do you understand this completely? Have you got this? So this all are the variations. This all are the variations where we are keep changing a k by somehow, that either we break the spring into smaller segments, or we connect those segments in series, or we connect those segments in parallel, or we use two springs in series and parallel, and this all are the variations. This all are the general variations of the spring. Now let's try to vary the mass and let's see how the effect occurs. Let's have a look. Let's suppose the question is that it is the situation, this was the spring, and with this spring a block has been connected. A block is having mass m1 and this spring is having a spring constant k. So initially block m1 oscillates with time period t1, with time period t1. Now next instant happens when this happens. It's a block, a spring having spring constant k. This was m1 and this is block m2. So the next instant is if block m2 is put on m1 when it passes through mean position, when it passes through the mean position. Find out new time period, that is what we call as a T2. Yes, as well as take a ratio of T2 is to T1. Yes, this is the requirement, that initially only the one alone block were there, and this block is used to oscillate with the spring. A spring constant is the K, and now then what happens, that you have put up one more block, which we call mass M2 on the M1. When it passes through the mean position, we need to find out the time period. So how will we do this? What could be done? Yes, what is to be done? What do you think? So what I understand is that initially only the situation was that it's a spring were there, and only M1 was there. It's a T1 which is equals to 2 pi root of M1 divided by K. When we have added one more block to this system, it's an M1 on this, and this is M2 on this. So it is the situation where T2, which is equals to 2 pi root of M1 plus M2 divided by K. If such is the situation, then I can have it's a T1 is to T2, which is equals to under root of M1 divided by M1 plus M2. As I have been asked T2 is to T1, I will just inverse this ratio. This is equals to root of M1 plus M2 divided by M1. I hope this is clear. Is it clear? Is it? Are you sure? Do you have any doubts up till now? Is there anything? Is there? No? Then shall I add something? Shall I? Let's have a look. This is very interesting. The question says that in the previous question, when only block M1 oscillates, it is having amplitude A. Find amplitude, let's call it A dash, of oscillations when both the blocks were present. So what could be done? What do you think? Take your time of 10 seconds and just try to think that what could be done in this situation, that when they said that one more block has been put up, and when one or more block has been put up, what would be the situation? What do you think? What do you think? What could be done? Yes, anything? Anything? Do you understand anything? What would be the situation? Any idea? No? So when they say it that the block, look at this, a block of M2 is put on M1 when it passes through the mean position. So at mean position, acceleration of blocks performing SHM is 0. So force acting on it is also 0. And if force acting on it is 0, that means momentum of the system can be conserved. Yes, it is the principle of momentum conservation, that if no external force is acting on the system, then total momentum of the system can remain conserved. That means the initial momentum should be equals to final momentum. If it is the case that initial momentum and final momentum would be equal, then what is the initial momentum? It was only the one alone block, and there was m1v. That is equals to, now two blocks will be there. It's an m1 into m2. This is v initial, and this is v final. I hope this is clear. Is it? So when I have it's an vi, I can write it's an amplitude a multiplied by omega initial, and this is equals to m1 plus m2 multiplied by amplitude dash minus multiplied by omega final. Yes, what I have used v is equals to r omega, and r is the extreme position. I hope this is clear. So when this has happened, the situation will be m1 multiplied by a multiplied by omega. Now what can you write for the omega? What do we option? So we have this option that we used to write it's a k equals to m omega square, and from this it's an omega square which is equals to k by m, or it's an omega which is equals to root of k by m. Yes, so this is simply the k divided by m. Here it was the m1 equals to m1 plus m2 multiplied by a dash multiplied by omega final, that is equals to root of k divided by m1 plus m2. I hope this is clear. So if this is the situation, let me, yes, if this is the situation, what I need to do is that this is m1, this is m1. If I solve this, it is a multiplied by 1 by root of m1. This k and this k would be cancelled out. That should be is equals to, this is a dash, this is m1 plus m2, this is square root of m1 plus m2, so this is equals to square root of m1 plus m2. From this it's an a dash by a, that is equals to root of m1 divided by, this is m1 divided by m1 plus m2. Yes, this is the question, and this is your final answer. Got this? Do you understand this? Have you? Do you like this? Great. Ready for one more question? Are you ready? Let's have a look. Suppose the situation is something like this. This is certain container over there, and this is a spring, this is the rigid surface, this is the k, and this is the m. This is the initial system, and after certain time it has happened something like this, that one more block has been arrived over here, as this is spin spring. So let's call this time period as a t1, and let's call this time period as a t2. So first they will ask me that find out ratio of t2 is to t1 for system performing SHM. You need to find out the ratio for the particle who is performing an SHM. So how will we do this? It is as simple as that. This is t1, which is equals to 2 pi root of m by k, sorry, it's a small m, and this is t2, it is simply 2 pi root of m plus m divided by k. It is as simple as that. So you can do this easily, that I understand, t2 by t1. Now the next question is interesting, that if this oscillates, The question is that in the previous question, in the previous question, find out maximum amplitude of oscillation so that block having mass m can safely oscillate and does not thrown away from the piston having mass small m. So go through the question. What can be done? What can be done? What do you think? They said that in this situation, find out the maximum amplitude of oscillation so that block which is having mass m can safely oscillate, and this is, they are talking about this situation. Yes, this can oscillate safely. As it is moving, it is going to oscillate in downward and upward, and this would be the situation. So what could be the maximum oscillation of the system so that this is not going to be thrown away by this piston mass m? How will we do this? What can be done? Yes, so what I understand is the maximum acceleration due to which a maximum acceleration could be equals to minus of omega square into a. When I say maximum, that's why I have written it a. Otherwise it was a is equals to minus of omega square x, but omega never changes, only x could be changed, and it is the maximum displacement, and that maximum displacement is what we call as an a. So this a max is equals to minus of omega square into a, and if this a max is less than or equals to g, yes, it's a gravitational acceleration, then block m always safe to oscillate. I hope this is clear. So if maximum acceleration is less than or equals to g, then this block m would be always safe to oscillate. I hope this is clear. So in this situation, what we need to do is that let's copy the value of a max. So this is the situation, minus of omega square a should be less than or equals to g. Yes, this minus represents the only the direction, because it represents an oscillation happens due to the restoring force only. So basically this is omega square into a should be less than or equals to g, and if this has happened, it's an a should be less than or equals to g by omega square. Now how do I replace this omega? We have the oscillation time period as t2, which is equals to 2 pi root of m plus m divided by k, and if such is the situation, then this is equals to 2 pi by t2. This is 2 pi by t2, which is equals to root of k divided by m plus m, and if I'm going to square this, it's an omega square, which is equals to k divided by m plus m. So this is the simply a should be less than or equals to g divided by omega square, which is equals to k into bracket m plus m. If amplitude of this oscillations is less than or equals to this, if amplitude of this oscillation is less than or equals to this, then this block is never ever going to thrown away from the system. I hope this is clear. Is it clear? Is it? Are you sure? Correct. Ready for the next question? Are you ready? Shall we? Great. Let's move on to the next question. Let's say this is the system and this is K. A block is having mass M. It says if block M performs SHM, find out amplitude of SHM. You need to find out the amplitude of the SHM. How will you do this? What could be done? What could be done? So if I will hang up this block initially, then the situation will look alike that this is the spring. Yes, and this is the block M. So it was the original spring and this is the extension. So whatever the forces that are acting on the system is, it's an mg because of weight, and restoring force which is equals to kx. As we know that at the mean position, this mg and kx would be equals, because at the mean position net force acting on the block is 0, and if it is 0, this is mg is equals to kx, and from this it's an x which is equals to mg by k, and that could be the amplitude. So amplitude would be equals to mg by k. I hope this is clear. This would be the capital one. Yes, this is the mg by k. I hope this is clear. Is it clear? Is it? Now do you have any doubts? Is there anything? No? Great. Let's look at the quick questions. If a spring of spring constant k is cut into n equal parts, then the spring constant of each piece, let's understand this. Let's say this is k and this is the L. This segment has been divided into certain equal parts, and I have took one of the piece of them, then this is k dash and this length will be the L by n. So we have the relation, it's a k1 L1 which is equals to k2 L2. So this is k multiplied by L, and this is equals to k dash multiplied by L by n. This L and this L has gone, and this is k dash which is equals to n into k. I hope this is clear. Is it? Great. So this k dash will be equals to n into k, and this is the spring constant of each part. Got this? Great. Ready for the next question? Let's have a look. The time period of spring mass system is independent of, it's a t is equals to 2 pi root of m by k. So it does not depend on the place, it does not depend on the medium, it does not depend on the temperature as well. So it depends on, it is independent of the both, it's a place and a medium. So that means this is the correct answer. I hope you got this. Do you? Are you sure? Great. So let's wind up this session over here. This was all about the spring block system SHM. Basically the total SHMs or the total cases of SHM we discuss is SHM due to both two systems only. One is this SHM due to spring and block system, and another is the SHM due to pendulum. Yes, so this is one of them, and this is having a very good amount of probability to be asked. So please go through this carefully. Please do at least as many questions as possible. This will help us to get the good numbers. Thank you. Have a good day. Take care.